Good afternoon. Today I will present some exercises from our chemical calculations worksheets as well as their stepwise solution. The first exercise I will present is exercise 30, which deals with the synthesis of Prussian blue. Prussian blue is a dark blue pigment, which you can see right here. This is what it looks like. And it is industrially prepared in a 3-step process. So in the first step, iron 2 sulfate heptahydrate is treated with sodium hexacyanoferrate, decahydrate, and ammonium sulfate. The products are Prussian white, sodium sulfate, and water. For the second step, the following reaction takes place, which you can see written here below. So our first task, task A, is to assume that the yield in the first step of the synthesis is 93% and in the second step is 96%. We are to calculate the minimum amount of sodium hexacyanoferrate decahydrate, which is from the first step, that is required for the synthesis of 4.51 grams of the final ammonia double iron complex that we can see here, this one. So, the very first thing that I did was I wrote down the equation for the second step of the reaction again, as well as the individual yields that we know for both of the complexes in the steps. So here you can see that, and we are asked what the minimum amount of the sodium from the first step is required for the synthesis so that we have 4.51 grams of the final complex in the second step. The first issue that we have to address is the ratio of the different complexes in the first step of the synthesis versus the second. So when we look at the equation in the first step, we see that the ratio of the sodium complex to the produced iron complex in the first step is 1:1. Therefore, in theory, the ratio of the sodium complex, again from the first step, and then the final iron complex that we want in the second step should also be 1:1, or in this case 6:6 to have the correct stoichiometry if we would look at the equation. However, reality is different. In reality, in the first step, the yield was only 93%, as we were told, so not a complete 1 or 100%. The ratio of the first step would therefore be 1 to 0.93. We had one sodium complex that gave us 0.93 of the resulting iron 1 in the first step. This means that in the second step, we have the 0.93 ratio of sodium complex and the final iron complex, which had a yield of 96%. But since we are doing this ratio not 1:1, like theory, but with the actual ratio of 0.93, we have to change the final ratio. The real number of the final iron complex will be the sum of the starting 0.93 sodium complex and the actual 0.96 yield of the final iron produced. So what I did to get that actual ratio was just I multiplied 0.93 times 0.96 to get the real ratio of the final iron complex, which would be 0.8928. Now we can finally write the final real ratio of the initial sodium compound to our final double iron complex. It will be 1 because we started with 1 sodium complex from the first step. That is still the same, that didn't change. But the real ratio of the final iron complex was 0.8928. Now we can get to the actual calculations of how much grams of sodium of the sodium compound we will need. Firstly, we have to know how much moles these 4.51 grams of the sodium compound are. For this, we just follow a very simple equation that says that the amount of moles, N, is equal to mass of the compound divided by its molar mass, which can be deducted from the periodic table. So here our mass of the product is 4.51, that was given, and the molar mass of the double iron complex from the second step is 285.1. I inserted both of these values into the formula and I got 0.0158 moles of the final iron complex. So we know that 4.51 grams are 0.0158 moles. Now we can do a comparison, which I have written here. We can do a comparison of the first step versus the second step. We know that 1 mole of the sodium complex from the first step gave us 0.8928 moles of our final iron complex. This is seen in our ratio. We can just take the same values. And now we want to know how many moles of the sodium complex will give us 0.0158 moles, which are the moles of the 4.51 grams which we actually want. So we solve this equation for x just by dividing this value by this value and then times 1. So it will be 0.0158 divided by 0.8928 times 1. And we get that x is 0.0176 moles of sodium complex needed from the first step to get this amount of moles of the final iron complex. So now, since we have the moles, we can very easily get to the actual mass. We will use the same simple formula that we used before with the moles, except now we will transform it so that it gives us mass. So mass will equal the number of moles times the molar mass, which I just calculated here from the periodic table, that equal to 483. And when I times these two values, I got the final result of 8.54 grams. So in order to get 4.51 grams of the final double iron complex, we need to start with 8.54 grams of the sodium hexacyanoferrate complex to get this. So that was A. And in B it is said that for the synthesis, only 5.81 grams of sodium hexacyanoferrate decahydrate with a purity of 97% and 8.79 grams of soiled sodium hexacyanoferrate decahydrate with a purity of only 65% are available. We have to calculate the masses of these two different sodium hexacyanoferrates in order to synthesize the 4.51 grams with the yields given in A. So this is telling us that for this synthesis we have two kinds of the sodium hexacyanoferrate available. We have different amounts of them and we have different purities. So firstly, I just wrote all of the values that we know again here. So this is the mass of the first sodium available. We have 5.81 grams and the purity is 97%. The second sodium that we have available, the soiled one, we have 8.79 grams of that and the purity is only 65%. And so in A, we calculated that we need 8.54 grams of the sodium complex, and we assumed that it was 100% pure because it wasn't specified otherwise. So the first thing we do whenever we have a given mass of something, of a compound with a purity percentage, is we have to find out the actual mass of it. And this we do by multiplying the purity percentage, which we firstly have to divide by 100, by the mass. So here you can see that for the first sodium available, it will be the mass that we have given, 5.81, times 0.97. So the actual weight of the first sodium available will be 5.64 grams. And since its purity is so high, it is 97%, it's very high, and we want the purest compound possible, we will take all of it. So the whole amount that we calculated here, the whole 5.64 grams, will be used for the synthesis. Now we have to calculate the mass of the 65% sodium that we need for the synthesis. So for that we will do the original pure mass of the sodium complex that we got from A, because that's pure, and minus the mass of the 97% sodium. This is 2.90 grams, which is the mass of pure sodium. By pure here is meant that, by pure sodium here is meant the 65% of, the 65% portion of this sodium that is pure, because we know that it is 65% pure. So this means that 65% of it is pure and 35% is impurities. And these 2.90 grams are the 65% pure portion of the sodium. So I again did a little comparison here. We know that 2.90 grams are the 65% pure sodium. So we wonder how many grams will be the, quote, 100% sodium, meaning that it will also have its impurities in it. And I just divided these two numbers again times this one, and I got the result of 4.46 grams. So we would use 5.64 grams of the 97% sodium and 4.46 grams of the 65% sodium for the synthesis. Thank you very much for listening. This is the end of my explanation on how to do exercise 30. I hope you enjoyed.